Check 1, 2, 3, 1, 2, 3, 4.
Well, I just don't want to like mess up, spoil your presentation if you have like a. Yeah, I think you're right. That means probably not.
Okay, sounds good. How do I put this back to where it was? You know, I just click on that middle.
Good morning, everybody. This is just a 1-minute warning to get a coffee refresh if you need it. Find a seat. Still have a bunch of seats over here. A bunch of seats everywhere. Wow, everybody got really quiet. I guess I'll just go ahead and get going. I'm Erin Robinson. I'm the Executive Director of ESIP, and this is the ESIP Summer Meeting. I just, actually, sorry. Always has, just a little technical glitch so that I feel like I'm sort of back to my roots. So, as some of you know, when we were at the winter meeting, we had an exercise or a group activity around pulling together a timeline of different things that have happened over the last 20 years. So, ESIP turned 20 last year, it was founded in 1998. And I wanted to run through some of those highlights to give you a sense of where we've been and where we're going. So in 1994, NASA ESDIS started serving data. As I mentioned, ESIP was founded in 1998 by NASA GEO started in 2005. That's the group on Earth observations, bringing together now over 100 countries working to share Earth observations. ESIP created the data citation guidelines, and I think that that was really one of the first products that put us on the map, where then people here started taking the data citation guidelines back to their home institutions and actually implementing. Coptis is a group of publishers and data repositories that comes together around how we share data in publications, and they had a commitment statement. We then built on that commitment statement more recently through a project that AGU convened called Enabling FAIR. And that commitment statement now has the data citation guidelines from ESIP built into it, and is trying to change the way that scientists are publishing their data when they publish their papers, and giving everybody a consistent interface to that. EarthCube started in around 2010. The data fairs at the society meetings like AGU started around 2015. The Research Data Alliance has come along since then. I think it was founded in 2014. And then in 2013, so this is a little, my animations are a little all over the place, but starting in 2013, ESIP was talking about schema.org, and that stretched through this meeting. And yesterday we had a great geosemantic symposium, which is continuing to build on that work. And ESIP now has something called Science on Schema.org that the Semantic Technology Committee has been working on. And then another sort of recent update this year is that the data stewardship community of ESIP has come together for revising the data citation guidelines. So there's a current version 2 that's out on the street. And then in January, we had the Open Government Data Act that was passed. And all of this, I think, leads to the fact that ESIP has a tagline of making data matter, and that as a community, over time, what we've seen is that we have consistently made data matter. And some people might even say that we could check the box that data matters, that scientists think data matters, and that now in this meeting we have the theme of data to action. So again, coming back to our 20th anniversary work, we had an interview series, and Rama Ramapriyan is here in the room, and this is one of my favorite quotes that came out of that interview series, that being able to implement things that you thought about 20 years ago because of the computational capability is available is really exciting. I think it's so exciting. I think it's amazing that we're at this point of data to action, and that all of us are doing that. And ESIP's sort of part in that is being the collaborative fabric. So it's meetings like this, it's the collaboration areas that happen all the time, and you'll hear more about that later. But it's bringing people together at this connective layer, that's where we sit, and helping people network. And so what we don't do is we don't provide data, we don't sustain cyber infrastructure, compete with our members, or develop standards here, but we do encourage conversations on all of those things. So that leads us to where we are today, and this data to action theme. Our strategic goal that this is supporting is increasing the use and value of earth science data. And so there's some things that are going on this week about that sort of support this theme. So one of them is the teacher workshop. Margaret Mooney and Shelley Olds are here, and they're teaching teachers how to use Jupyter notebooks this week. So it's how do we get data into the hands of teachers? We have the disaster lifecycle group that's been developing something called operational readiness levels to get data, to be able to indicate how data is being used, can be used for the public and private sectors. We've been working with Amazon Web Services, AWS, through the lab, which you'll hear about a lot on Thursday. But again, it's data to action. It's how do we help researchers use and analyze more data and different kinds of data. The Google Dataset Search is another example of, I think, data to action that we can talk about. And then the Data Management Training Clearinghouse is another thing going on this week. So there are many different dimensions. The training is, a way that we enable researchers to better manage and steward their data. So all of these are different dimensions. And I think when I first thought about data to action, I thought maybe of the upper left, the kind of traditional approaches, but there's a lot of technical underpinning that's needed to make data actionable. So with that, I'd like to end by introducing my staff, the ESIP staff. So I can't do this alone, and I'm really fortunate to have a talented team. So Annie Burgess is the lab director. Annie's in the back of the room. Megan Carter is our new community director as of October of this past year. Megan is right here. And then Dan Keys is our operations and logistics coordinator. He's the one that makes the remote meetings go and is streaming this, and Dan is also sitting at this table. We could just give the team a round of applause. And then I'd also like to acknowledge the Capitol Meeting Planning team. Matt Burdetsky leads that team. They're at the registration desk. They're also helping with the room setups and the AV, and they're really what makes this meeting run seamlessly for us. And with that, I would like to hand over the microphone to Carl Benedict, ESIP's president. Thank you so much.
Thank you. And I'd also like to echo the amazing gratitude to Erin and Annie, Megan, and Dan for their incredible contributions in supporting our community. We talk a lot about the contributions of and activities of our various collaboration areas and the volunteer activities that ESIP contributes to and the products that we generate. But that would be impossible without the support and the strategic focus of our staff members. When we were in yesterday's board meeting, the board in particular wanted to make sure that we acknowledge and recognize the critical contribution that our staff makes to enable all of us to be able to do the work that we're doing in being able to focus on the science, technology, decision-making, and other activities that are the things that interest us and that allow us to talk about being able to go from making data matter to actually going to converting to action. And so it's a tough balance to maintain in terms of the amount of staff support that's needed to support a very active and engaged volunteer community. And ESIP has been incredibly successful in being able to achieve and maintain that balance for now 20 plus years. So thanks again to the staff for helping us as we now focus, as I'm talking here, on the people. We talk a lot about the community, but the community is made up of a lot of dedicated individuals. And we're going to sort of work in a Russian doll style out from some of the more visible participants in our community to ultimately recognize the contributions that everyone in this room and beyond is making to the success of ESIP and meeting our mission and objectives. So I'd like to start by recognizing our elected leadership. As a part of that, we have a board of directors. As I mentioned, we met yesterday. And that board includes the elected officers of ESIP, our governance chair, partnership chair, finance chair, nominations committee chair, and president, vice president, and 3 additional at-large board members. So I'd like right now for all of these folks to stand up and be recognized, and also to be recognized so that if you have any questions about how we handle sort of the business of managing ESIP, it's the board that has the responsibility for working very closely with Erin and the rest of the staff to make that happen. So if you please stand up and be recognized. Excellent. Thank you very much. But we also have additional elected leadership that are chairs of our other key committees, including data stewardship, education, information technology, interoperability, and semantic technologies. And the addition of these key players into the organization provide us what we call our program committee, which is a broader opportunity to engage with the community leadership when it comes time to examine opportunities for interconnectivity between the activities and focus areas for ESIP, and an additional way to get input and vet, whether it's policies or procedures or new documents or plans or strategies for ESIP. So I'd like Ruth, Becky, Dave and Lewis to please stand up and be recognized for their contributions as well. Are they here? There we go. Excellent, thank you. But of course, that's only this core of folks that have shown up in various leadership positions that are some of the more visible folks that sometimes across the stage here during our plenary sessions, and certainly engage in some of our broader outreach activities. But the work that's being done by ESIP on the ground is in our collaboration areas, our clusters. And we often focus on the clusters in terms of talking about them in terms of the topics that they address, as we see in the circle here. But it's even more important to think about the people, the contributors who are leading those and coordinating those clusters, because it's the engagement and investment that leadership has in those collaboration areas that is really where ESIP gets its work done. That's where we have the important conversations. That's where we bounce ideas off of each other. That's where we come up with innovation, and that's how we move the ball forward in terms of meeting a lot of parallel objectives. And if you see the topics that are addressed in our different collaboration areas, it's a long list. And without the investment of all of our chairs and co-chairs, this work wouldn't be happening. So as we're getting our workout for this morning, if I could ask all of our collaboration area chairs and co-chairs to go ahead and stand to be recognized. So as these folks are standing, take a look and see who you might be asking how you might be able to help. If you're interested or have a question about how our collaboration areas operate, these are the folks that are first and foremost in helping to lead those activities. So don't be shy to ask questions and step forward to help out. So ESIP, for me, has always been a unique organization in terms of the diversity of interests that bring us into the community. And we can see here the expressed areas of interest for the folks that engage with ESIP. But I think it's even more important to think, and it's kind of hard to read here on the bottom, but if you start to tally up those numbers, that's much higher than, say, the 300 plus folks that have registered for the meeting, suggesting that ESIP is an incredible venue for not interdisciplinary work, but transdisciplinary work, as we are typically here and interested in a multitude of different but somewhat related subject areas. And ESIP is a tremendous venue for being able to exercise that or scratch that transdisciplinary itch that many of us feel. So, when we think about, the 1,500 or so areas of interest that are expressed by the 300 people that responded to this question, that's a pretty rich area of overlap, of opportunities to exchange information and interests and knowledge across disciplinary and interest boundaries. And that's actually one of the primary strengths that ESIP brings, as it brings in participants in the entire value chain of earth science data and information. And it's only in this particularly rich environment that we're able to have that exchange that really grows and extends beyond what may be our traditional areas of focus back at our respective organizations. One of the other areas where ESIP has been incredibly effective is fostering the next generation of earth science data and information professionals. And our Community Fellows program has been particularly impactful in that way, as we have had a number of our fellows that have continued to engage as they've moved beyond their educational activities. And they continue to come back to ESIP. They continue to contribute to ESIP, and they take their ESIP experience into the organizations that they then go into after they finish their education. So I'd like our current cohort of ESIP fellows to please stand. our fellows are here both to contribute and learn, but also contribute. They're bringing new insights and perspectives into the conversations that we're having in our community. And they are going to be the leaders of the next generation of work that we're doing here in ESIP and that we take out more broadly. We also have those of us that have, I like to think of it as experienced ESIPers, who are here to answer any questions you might have. So take a look as you're going around the meeting. Look for some of these ESIP Ask Me buttons. We are the ESIP ambassadors. In addition to the officers and leadership that I've already introduced, take a look, and if you have any questions about how ESIP operates, how you can engage and participate, don't hesitate to ask us, because we have a broad and diverse experience with ESIP, and we can definitely help you figure out how you can fit into the organization and make your contribution and find your location. ESIP is not just the community that's here, though. We're also continuing to grow. We have a number of new ESIP partners that have joined ESIP in the last 6 months since our January meeting. And I'd like any of our new ESIP partners that we have up on the screen to please stand and be welcome to the community. And the growth of ESIP is critical because, again, we thrive on new insights and participation. And it's our new members that are both demonstrating the value that they see at ESIP and also bringing new contributions into the community. And this is key to keeping ESIP vibrant and active. And we're very happy to see that. We're also, of course, continuously thankful to our sponsors, NASA, NOAA, and USGS, for providing the foundation of support for ESIP as an organization that allows us to actually have our staff and be able to provide the venue for us as a community to meet and coordinate and do the work that we'd like to do. So I'd like to thank our sponsors as well. Of course, ESIP is not alone, and ESIP has connectivity with a large number of other organizations with similar or overlapping interests. And some of the connections that we have that in many cases are long-standing include the co-location of meetings and the perceived value and real value of being able to bring representatives from multiple communities together into a shared venue. And this is where we're actually seeing an increase in the number of co-located events with ESIP, whether it's the Data One community meeting, the LTER or IGSN activities, or the Council for Data Facilities. This is all a set of activities that allow us to cross-fertilize between ESIP and other organizations in a very intentional way that allows us to identify areas of shared values and interests, and being able to identify opportunities for us to bring members of our communities together to further enhance the conversations and insights we can gain and the impact we can have. So overall, ESIP as a community has a number of strategies for being able to achieve our strategic goals. That certainly includes what we're doing this week in terms of our in-person meetings and workshops that we otherwise organize throughout the year. But our collaboration areas in particular also meet regularly in between our face-to-face meetings. And those are critical times for engagement, for continuing to make progress and achieve things between these what are often working sessions as a part of our twice annual meetings. And those are key to continued engagement and activities in ESIP, and I encourage you to participate in those. We also have our phenomenally successful ESIP lab activities, which have been great at providing some seed funding which, you know, I've often thought of, certainly talked about this in the context of our Funding Friday Awards, but I think our ESIP lab is very much in this spirit as well, in terms of providing a framework for being able to allow many of us to scratch a particular itch that we have, that without a little bit of funding, whether it's logistic funding for some cloud computing, being able to pay a little bit of a graduate student or somebody else to work on a project, is just enough to be able to move a project forward that also allows us to create connections, not just within ESIP, but also with additional collaborators outside of ESIP, further increasing the impact and connectivity of ESIP with the rest of the earth science data and information community. So whatever your particular preferred interaction mode is, in person, online, through projects, ESIP has a place for you to be able to do that and to participate in the community. And with that, I will pass the torch to Mike Daniels.
Hi, everybody. Welcome to Tacoma. You don't have to walk too far from this place to find out there's a lot of interesting sights to see. So I hope you get out and take a look at this city and the environment that we're in. Today's meeting, this week's meeting, is really one of the larger meetings we've had. 11 plenary speakers, 53 posters, 90 sessions, 96 first-time attendees. That's really cool. That's like 1/3 almost. 159 session conveners, international partners from Europe, from Australia, and basically over 300 attendees. At this time, in following everybody's tradition for standing up, I'd like to ask the 96 members that are new to stand up, please. Come on, all of you. Excellent. Great. Thank you. So in our board meeting yesterday, we talked about our first experiences with ESIP, and this is mine personally too. You're in sessions and there are things that I didn't understand, I'd never heard of before. That's going to be normal. But the real key is this is a place where a data professional can be at home. I was in an observational science facility with instrumentation that they bring online all the time. Some of it had tons of data, and I was always asking, what about the data? What are we going to do with all this data? And so this is the place to ask those questions, and you really can build upon the support of the folks that are here. So the last thing I'd ask people to do is please introduce yourself. We'll take a minute for people to introduce yourself to one person that you don't know. Do that now. Okay. Thanks. Right. Okay, thanks everybody. We'll wrap up and have some time at the break. Thanks. Oh, there's some crickets chirping. I did not do that. Okay, I'll get back to the agenda. I'm really cool. I'm really glad to see people collaborating and introducing themselves to each other. So the meetings, the meeting at a glance, you can see from this slide here. We definitely have plenaries every morning to bring people together. We have a lot of break time. That's a pretty much a part of the culture of ESIP is to have break time to allow additional collaborations to build organically. Much of the meeting is in breakout sessions, and we really encourage people that if this breakout session isn't working for you for whatever reason, please vote with your feet. Go to another breakout session if you feel that that would be more valuable. On Wednesday night, we'll have a reception and a research showcase, which is kind of a creative take on a poster session. And then for those new members, I encourage you to attend ESIP 101 at lunch today. Either new members or members that would like to know a little more about ESIP. That's at lunch today. Is that here? Okay, this side. A couple things. One of the really cool things about ESIP for me is they're always trying creative new ways of doing meetings. And one of these creative ways is called the unconference, which you may have heard of at other meetings, but maybe not. Essentially, an unconference is adding things to this conference that were not sessions originally planned, but sort of came up during other discussions. And so people will have an opportunity to think about what you might want to propose and submit that as a sticky note. On Thursday, the last Thursday afternoon breakout will be this unconference session. So people will give a pitch about their session, and then they'll establish the room locations for those. So as you're going through the meeting, if you have an idea that you didn't think was represented in the meeting's agenda, propose it at the unconference, and then make a pitch for that for an informal and very spur of the moment kind of get together. Another cool thing is the Funding Friday. So what this is about is on Thursday evening, we're going to go to a pub, and you're going to have poster boards, you're going to have markers, you're going to kind of collaborate with some hopefully new people that you haven't collaborated before with, and draw up a poster, just hand sketch a poster and an idea for an award that ranges from $3,000 to $5,000, depending on if you're a student or a full-time person. And it'll be, you basically give your pitch for this poster that you made the night before on Friday morning, and we'll do a walkthrough, and then they'll pick some winners of that, and right on the spot you'll be awarded these $3,000 to $5,000 awards for a creative idea. Many of the things. What's that? I guess we're gonna vote for $3,000 to $5,000. Yeah, that's it. Yeah, $3,000 to $5,000. Thanks, Shelley. Money. And by the way, you don't have to participate on the Thursday night event. You can just bring your poster Friday, but it's really fun. You got to go on the Thursday night. And on a serious note, the ESIP does have a code of conduct that everybody should read. Especially look at this link at the bottom. We're a community that really supports inclusion, diversity, fair treatment, and good treatment of people. So we do have a code of conduct, and there are various ways to report concerns about the violations of code of conduct, including talking to the leadership. There's an email address here and a form that you can report these issues anonymously. But please, let's be civil to each other, and it's a great meeting time, and it's made even better by following the code of conduct that we have. We're doing a sustainable meeting. The city of Tacoma has a lot of sustainable items, including recycling stations and sourcing local food, which you'll see as you work within the city, bringing your own mug campaign, a free tram, and then ESIP in particular has some sustainable meeting ideas like paperless meetings. There's a lot of remote participants that will be connecting to the sessions. We'll have a climate conscious fashion show, which I'm going to call the Sustainable Clothing Demonstration on Thursday. And then ESIP's limited in swag. And so, some of the fashion show ideas are using repurposed clothes that you purchase at a thrift store, like the shirt I'm wearing right now. And basically not buying everything brand new. And by the way, when you go to a thrift store, there's a lot of good vinyl there too, if you want to check out that stuff. Some of the meeting technology we use Sked to lay out our meeting. It's a really cool tool. You can get an app on your phone to look at your meeting schedule. We use GoToMeeting for our conferences, which is very ubiquitous these days. We have Twitter, so please tweet to the ESIP Fed hashtag. All of the sessions are recorded, and we ask people to please put some takeaways in these sessions. These are the artifacts of the meetings that people can go back to, especially people that weren't able to make this meeting. And then we have a Figshare portal that we also store our posters and other meeting artifacts. And interestingly, I had the circle there in the wrong place. This was pop up now, but it's very active. Over 4,000 views and over 1,000 downloads. And so it's a great way to share with the virtual community that we have in ESIP. So please contribute to that, and also use your ORCID if you have one. That actually helps link things together. So here are some of the meeting artifacts that we have that I mentioned: the session recordings, the presentations in Figshare, and the session takeaways. The fully expanded schedule will also be up when everything's been added. What we've just started doing this year, with the great help of Megan, is put together a meeting highlights. So if you're not able, if you have colleagues that you'd like to include in the meeting that weren't able to attend, that can actually attend this meeting highlights webinar, which will be a couple hours session, hour and a half session, to kind of go over the highlights of the meetings, and then point people to the meeting artifacts if they want to know more. So that's why these meeting artifacts are also important. And that'll be scheduled. The date is August 8th at 12:30 p.m. Eastern. I want to make sure we recognize our meeting sponsors. We have bronze sponsors, HU and ESRI. We have the Friends of ESIP. That would be the Associated Universities Incorporated. And then to Figshare, IdeaScale, and AWS, who are in-kind sponsors. And now I'll introduce Jeff Ciarto to come up and discuss our new lanyard. Jeff?
How's it going? I'm Jeff Ciarto. I am the User Experience Director at Element 84, and this is the third lanyard that we've done. E84 has been involved with ESIP for quite some time in a bunch of different roles, but personally this is my favorite thing that we do every year. And if you've been to other ESIPs before where we've done the lanyards, you'll sort of see the theme. They sort of all look like this with the alternating E84 and ESIP logos. And then generally the background is a different theme every year. So before I get into the details about this, I just want to give a shout out to Nelson Marhalo. He's our senior designer at E84. He's not here today, but he does all of this design work. And so he sort of deserves a shout out for the general design of these. So we based this year's lanyard on this image that we found of Tacoma and that sort of sunset. So the kind of bold colors that you're seeing today are the result of this image that he was able to dig up, and he sort of based everything on that. We've got some low poly mountain ranges. If you look really closely at the printing, you'll see that they are actually like polygon style mountain. And then we've sort of interchanged those with some flat icon imagery. And you'll also note the icons in the corner of your badge as well. So yeah, that's pretty much it. Those are the lanyards, and I just want to thank ESIP for kind of letting us be a part of this tiny little user experience piece for this conference. I think they make a pretty big impact. And yeah, that's pretty much it. I hope this lanyard will find a home on like your PIV badge or your home organization like lanyards. When you get back, I always like to see them on other badges when I go back to other meetings. So anyway, thank you.
Okay, so speaking of your badge, everybody should notice that they have a little symbol on the bottom corner of the badge. And we started this a couple years ago, sort of a matching icon symbol. Hi, Madison, your match. And so what we're going to do this year, because we have 5 different kinds of icons, is ask people to find the 4 different icons from yours, and that will be your team in sort of reflection of the diversity that everybody brings something to the table. And so when you find those other 4 matching icons, you go to the registration desk, you get a spin of the wheel, and there are prizes that you win. I'd recommend you find find four people that you don't know or haven't worked with before. That's how we're going to handle the memory game. Pardon? Oh, you have to find 5. Excuse me. Yeah, because there's 6 up there. Oh, sorry. That's what a data guy gets for not paying attention. 5 other people. What do you win, Aaron? Lots of stuff. Some are secret. We can't share. But that's all I have for my part. Does anybody have questions? Have microphones? Okay, great. If not, I would like to introduce our first plenary speaker, Rob Casey. He's the IRIS Data Management Center Director of Cyber Infrastructure, Deputy Director of Cyber Infrastructure. Rob currently serves as the Deputy of Cyber Infrastructure at the Incorporated Research Institutions for Seismology, also known as IRIS. That's a local partner here in Washington, state of Washington. His responsibilities include the management of software development and data services activities, as well as leading efforts to continually improve and expand the accessibility of a 0.5 petabyte data archive to the global scientific community. Rob has worked at IRIS for 25 years in many different capacities and has developed software to author seismic metadata, discover data for earthquakes, and federate bulk data requests to international data facilities. As Deputy Director of Quality Assurance, he led a talented group to build a 10 terabyte analytics system for continual quality tracking of the entire DMC's data holdings called Mustang. Rob graduated from the University of Washington with a bachelor's degree in electrical engineering.
Thank you, Mike, for that introduction, and thank you, Megan, for getting me set up with this. I appreciate having the opportunity to be the first speaker for this summer meeting. It's a wonderful, I'd almost say honor. I do really appreciate the opportunity to speak about improving the value and reach of seismic data, and I'm just going to focus kind of on my science in the theme of what this this meeting is about, which is increasing the usefulness and value of data. So IRIS is a consortium of more than 100 universities in the U.S., and then we have partners from all around the world that are part of our community. And IRIS is predominantly funded by the National Science Foundation through the SAGE program. So how many here have heard the term data lake? Raise your hands. A lot of people. Yeah, this is a term that was coined a few years ago as people started to recognize that there was a huge amount of data that was starting to get generated by various things that would be sensors or collection of metrics from users' activity. And so this term data lake started to come up because centers needed to find a way to be able to store all this, and they were confounded by the inability to be able to actually structure it. So the notion of a data lake is to have just a very large repository of data that is largely unstructured, and it's very dependent on users to be able to go in and actually pull information out. Just to give an idea of scale, what IRIS DMC works with, we currently hold about 550 terabytes of seismic data, and we have more than 500,000 seismic channels. IRIS Data Management Center has their data a little bit more structured, but still a lot of it's stored in a fairly raw form. So what we want to do to make data more useful and have more value is we want to introduce elements that introduce structure to data and allow its findability and accessibility to occur. And so one of these is something that IRIS did as far back as 1988, and that was to set up standards of curation and exchange. And this started with our seed data format, which was created and ratified by the Federation of Digital Seismic Networks. And this is a very large consortium of international data centers. And then more recently, we started to move on to a more flexible data format. We realized that seed was designed for running on 9-track tapes. And in this age of really high-speed broadband networks, we needed something that was much more flexible. So we've started to move into the realm of XML-based formats, and we also still put out standard formats for the use of legacy software such as SAC and SegWi. And then we've also kind of gone back to the basics, and we try to reach out to a wider user base by adopting a CSV format that has some header annotations. Another way that we have managed to improve kind of the ability to traffic our data out of what would otherwise be a data lake is to introduce web services. And we first started this as an initiative within our own organization, and then we standardized the web service format after it was proven to work within our own facility. And so now the Federation of Digital Seismic Networks has actually adopted it for use in their home data centers. And so our primary job with these is to deliver raw seismic data, station metadata, and earthquake metadata. On top of that, our notion with web services was to provide server-side computational and transform capabilities. And so we wanted to provide ways that people could manipulate the data before they download it. And so there are some additional enhancements that we offer at our own center. On top of that, we have a quality assurance system that we actually examine how good our data is and how good the data is coming to us. And so we also put web services on those. And then finally, we generate higher level data products, or we actually collect them from outside contributors and provide web services to them. The whole idea with web services is it both enables a very simple form of access if you're doing it in a REST style fashion, something you could do through a web browser, but then allows you to do something that's very large in scope by using programmatic forms of access through Python, through R, even through just a shell script. So a third element I want to touch on, and I think kind of elevates the level of maturity of a data center, is to institute a quality assurance program. And so we decided to go from something that was initially based on kind of a just-in-time reading of our real-time data feeds, and we went to a full archive quality assurance mode that can continually refresh itself as the state of the archive change. And so the kinds of things we look for and we realize are important to both data scientists and for data providers, the network operators, are issues such as the completeness of the data, spectral noise, cross-correlation, the latency of the data as it comes into our archive. And we also check to see that the metadata is appropriate, the description of the instruments. And you can also actually check to see how the described orientation of the seismometers are with respect to how the data presents itself. So those are three ways that IRIS has kind of brought its way into a point where we can improve the flow of data to increase its use and value. And so with these examples you see on the side are some of the outputs you can get from our quality assurance system in analyzing a seismic data network. So what I wanted to do was present you a couple of interesting stories. They're large data experiments that we didn't start, but we were definitely a part of. And these were outside institutions, outside scientists that were trying to answer some big science questions using seismic data. So I want to first start off with Los Alamos Labs. They were doing an industrial noise analysis study, and they needed a lot of data from us in order to detect discrete spectral components of seismic noise generated by larger machinery. And specifically, they're interested in looking at the noise from windmills. As you know, because of the great movement towards having more sustainable sources of energy, there are more and more windmills appearing all over the place. You'll see a lot of them here in Washington State if you drive through the middle of the state on I-90. So the thing that they're finding is that wind turbines introduce their own oscillatory noise. And so they wanted to see what kind of effect it would have on instrumentation that would be close by. And so these folks went to Amazon Web Services, and they started to implement a multi-node compute system. And what they did was they just retrieved the data from us through our web services. And so they didn't have to download the data in bulk before they started their study. they did a very highly parallel operation using Python Dask. The idea is that they would keep the values that they developed from the seismoacoustic algorithms, and they would throw out the data. They didn't worry about keeping it. So the outcomes of this study was they just kind of did an initial experiment on a single workstation, and it took them 30 hours to process just 2 stations in Texas with 13 years of broadband data. So this was something where they realized running something in parallel was going to make a lot of sense if this were possible. So the second run was on 100 stations as from the U.S. National Seismic Network, and this was for a period of 10 years. And so if this were to run on a single workstation, it would take them 41 days. And as many of you know, it's hard to keep any one thing running for 41 days continuously. So the reliability and the time it takes to do this is very prohibitive for doing experimental work. So instead, a 20-node cloud cluster was set up, and it took only 30 hours. And the nice thing is, because of the bring up and take down model of web services, is that you can do this large computation at very minimal cost. It only costs them $30 to do this. And this is a large national facility. So there was a 32 times speed increase and about 60 seconds per station per year instead of 1 hour. So at the top right, you can see the result of that initial study, and they're able to show kind of where those signatures pop up. The latest analysis that's occurring, and a paper is going to be written on this, is that the entire U.S. transportable array, this was a large component of the EarthScope large program, they're going to run computations at a much larger scale. So they've already started to do this kind of processing with us, and they did some testing at 50, 100, 150 node counts. And what they found was that they were actually hitting the stops on what our network could actually turn over in terms of traffic. And so, you know, that's on us to kind of see where our limits are in terms of deciding what we can improve. But at 50 nodes, there was an additional 3 times speed increase that they were already seeing. And so this is a huge number of stations for a very long period of time. And so we're going to see the results of this at much higher resolution using a very large array program to see what comes out of this. So the takeaways of running big compute on remote data is that programmatic services, such as the web services that Iris puts out, enable very large-scale activities to occur over the network. And you can conduct large-scale studies with a minimum of hardware and a shoestring budget using the cloud. So you can sit here at the table with your notebook and run a job like this at very minimal expense. Our systems are there waiting for your traffic. And big data computing does not require storing big data locally. So on the flip side, there are the limits on the number of transactions per second that an on-prem data center can support, and it generally has to do with how much budget they have and how much capacity they can build in to handle traffic. Correlative or gridded studies, anything where you need to have a lot of the data present at the same time, tends to require that you run in more of the HPC style mode, where you have a large scratch disk space, and you do have to be able to just transport that data over and then run your compute all at once. Processing speed can be also bounded by the network, and so that's what we experienced, is that we could only take so much traffic. And so if somebody's trying to run some experiments and do variations, the reprocessing can be expensive. Reach to data. So I'm going to move to a second story, and I'm happy to answer questions about any of these at the end of the talk. The second one was a ground motion prediction study for LIGO. And so LIGO is the laser interferometer that was looking for gravity waves in space, which they successfully did. So the goal is to predict the ground motion and state of gravitational wave interferometer during the event of an earthquake. And so I'm quoting from that paper. But the idea is that these are very sensitive instruments, and a certain level of earthquake, even halfway around the world, can have an effect on throwing off the ability for the LIGO system to actually be able to determine an event out in space. So they term that lock loss. So what they wanted to do was to generate a prediction algorithm for disruptive earthquakes. So if something happens over in Russia or China that is a fairly large quake, based on the azimuth and distance and the magnitude, they wanted to see what the effect would be at the two sites that LIGO exists, which is here in Hanford, and the other one is down in Louisiana. So they generated a database from data that came from the US Array program for a 12-year span, and kept the quakes from MAX 60 to 91, so they could use it for their determinations. And they generate a predictive model for local ground velocity based on these quake parameters. This is a case where machine learning was put into use, and they tried 4 different approaches of machine learning to try to work out something that would form a model that would give them good local prediction to a remote earthquake. And they generate a database of more than 730,000 earthquakes from what is ostensibly a very large data set from us. So they managed to find a clustering mechanism that gave them a good prediction capability, found to be about 92 to 93% effective for both of the LIGO sites. So what they did was then they expanded this study, and they said, well, we're looking at the entire array of seismic stations around the U.S. Let's see how the prediction works for the entire continental U.S. And so this grid that you see off to the right is kind of an example of how those predictions have come about. And so what they're seeing is that this could be the first step to a study of having a better predictive capability for such things as an early earthquake warning system, which is something that's very much in the minds of people right now, especially in light of the LA quakes that happened recently. So the takeaways from this study is that sensor arrays are terrific for measuring geodynamics over a large spatial area. You have a very good aperture on a large landmass. And modeling studies require extensive number of measurements over a period of years. Machine learning, as you all know, takes a very large amount of data. And they drew this data from us, and I don't think we even knew that it was going on. We probably just saw a rise in traffic occur. But then this study comes about, something meaningful that applies to even a different science, a different experiment out of what we made available through our data center. So seismic studies have utility in assisting other disciplines, anything that's sensitive to ground motion. And so high volume agile data flow just requires, it enables explorations to be able to draw inferences. It's really an enabler for machine learning to occur. So I wanted to leave you with one final thought in including this talk. And it was something that kind of ties in with the data lake, data river. We want to acknowledge the root. Okay. So as you know, lakes tend to be fed by streams, and these all tend to be sourced from these wonderful high mountains. And what is the mountain in this particular case? It is all the people that have go out in the field. It's the scientists that develop the studies, that get the funding, that develop the experiment and mobilize measurements across the globe. And what we find is a difficulty for a large data center to get past is the notion that it's our data. So when these particular studies I was talking about earlier were occurring, what we were finding in some cases is that they would be thinking iris for iris data. And our reaction is to go, no, there are a whole lot of seismic networks and programs that you tapped into that really should be getting the acknowledgement. And so we've been working really hard for the past, well more than a decade to annotate and notify anyone who's doing an experiment that of the sources of data that we have, and to be able to provide who was responsible for that, make sure that they get attribution for And what we've been moving into with the Federation of Digital Seismic Networks is providing DOIs, the persistent identifiers for data, to those seismic networks. And so this makes it really simple for somebody to compactly cite them in their own work. And that way, we're just kind of the middleman. We're the person that facilitates this flow of data, but we are not the source. We're not the mountain. So thank you very much. So yeah, I'm open to questions.
Questions for Rob? Please use the microphones on the side.
Thank you for the talk. Excellent. You mentioned a little bit about uncertainty just in one piece of it. I guess I have a question relative to uncertainty or certainty. What do you see as the role of the repository in conveying to those people that are coming to it about the certainty that there is about the data, especially if we're trying to get data being used beyond the research community and by other users? Oftentimes they're kind of wanting to understand, what that certainty is. What do you see the role of the repositories in that?
I think it's one responsibility to execute a good quality assurance program and to at least show measurements kind of in their raw form. If you have the right scientists or analysts that can make determinations from them, sometimes those are good to annotate. What we like to rely upon is for the network operators to provide us any kind of metadata that may indicate an uncertainty, such as clock drift or a spike of the data or so forth. A lot of times they are truly the best source for determining what happened, because they can sometimes attribute it to what caused it. And so I think it boils down a lot to good quantification, and most importantly, if you can include it in a rich metadata system and express that to the end user. So the question is, can you require that of the data provider? All we can do is require that they meet the standards of the data format that we provide, but it would take a much larger governance push for us to have the demands of a certain level of uncertainty expressed.
You have time for one more question, sorry.
Yeah, so I thought the example you gave of, is this working? Parallel processing on the cloud was really cool with Dask, and you were pulling in the data from your service, if I understand it, right?
That's correct.
Yeah, and so I was wondering if you moved that data to the cloud, would there be issues with like a cloud performant, are there issues surrounding cloud performant formats for that type of data, or is it just the cost, or is it both? Or
Yeah, that is something I didn't touch on, but it's very much been, we've actually had a program called GeoSci Cloud where we were funded to try experimenting with that. And so we have a bit of an idea of how we could go about this, but commercial cloud is, we've shown it to be economically unfeasible to have a persistent data center there. But something like NSF's Exceed program has possible promise for us to be able to have persistent storage and locality of data to compute. We also might be able to form partnerships with other institutions that would simply help us cover the costs of keeping a copy of their data there. All this is actually being actively discussed because HPC is becoming a much more prominent and I dare say certain discussion.
Thank you, Rob. Carl will come back up.
So it's my pleasure to introduce the introduction of our Raskin Award winner. And this is a particular honor for me because in 2001, when I came to my first ESIP meeting in North Dakota, one of the sessions and groups that attracted me was our information technology working group at that time, or it was IT and I. And Rob Raskin was chairing that group, and I was immediately impressed and drawn in to participating in ESIP and to working with that group because of Rob's clear enthusiasm and engagement and ease of introducing newcomers like me to the community. And he had many contributions to ESIP in his time with us. And in 2012, we suddenly and unexpectedly lost Rob. And it was a terrible loss for the organization. And it was clear that his dedication was not just this quiet connection that he had with ESIP, but also his sister, in recognition of his engagement with the community, worked with us and contributed the funding to establish the Raskin Scholarship. And it's an ongoing award that we are so happy to be able to produce or provide to a young researcher or student with a particular focus in earth science or computer science to help bring them into the community and recognize their contributions. I'll ask Ed to come up and introduce this year's Raskin Scholar Award.
Okay, good morning, folks. I'm here to introduce the winner of the 2019 Rob Raskin Scholarship Award. That person is Kai Berg, who's sitting right there, and he's going to give us a nice talk in a few minutes. But I first wanted to acknowledge also that Rob's sister, Lisa Steele, came with us for the first time in many years to be part of this group here and to be part of this moment here to honor Rob Raskin's memory. So she's here with her daughter Jessica. If you see her around this morning, be sure to say hello. I believe I see her sitting over there, or perhaps I don't have my glasses on. Maybe Lisa, where are you in the house? Oh, you're way in the back there. Sorry. She's way in the back there by the door. And yeah, say hello to her. She'll be around at break. Hopefully she'll be around the whole morning. And say hello to her. And, she lives here locally, and it was her first opportunity in a long time to be able to attend one of these ESIP meetings. This moment in recognition of Rob Raskin. So we've invited her to past meetings, but of course, the logistics of travel, and she had a job too, and it didn't always work out. So again, getting back to this year's winner, Kai, I wanted to say I've been doing this for a number of years now, and this year the talent field was really quite wide, and it took us a good while to kind of narrow down and focus on the winner. But one person did stand out. Kai has done some really cool work in the past in the field of ontologies and connecting ontologies for connecting brain data sets and making them more interoperable. And one of the cool things he did was that he was actually working and has worked and is working with the suite ontology that was part of Rob Raskin's legacy, the ontology that he developed. So now Kai is a PhD student at the University of Arizona in the Department of Biosystems Engineering. He's going to give us a nice talk. So some of his more recent work has been focused on cyber infrastructure and in combination with data analytics and ontologies as well. One of the cool things he's doing is he's trying to connect, I think he'll bring out in his talk, connect the biotic and the abiotic world. And I don't think we've really seen too many talks or themes in past ESIPs. This is kind of new for us. And so we hope Kai, this is his first meeting. So Kai, welcome to your first ESIP meeting, and we hope that you can bring some new energy and insights and contributions to future ESIP meetings. So welcome Kai, and the theme of his talk is going to be bridging Earth systems and life science semantics. So welcome Kai.
Hello, thank you for the introduction. Can everyone hear me? Perfect. All right, so thank you very much. I just want to acknowledge it's amazing and crazy that I was selected for this. Thank you to the family of Dr. Raskin, and I just really hope that things that people like me do can help to contribute in his legacy. So here it goes. So today I'll be talking about helping to bridge Earth and life science systems and work toward interoperable microbiome data. Okay, so today I'll be talking about the FAIR principles. I'll be talking about ontologies, specifically the suite ontology, as well as the environment ontology. I will be discussing the field of metagenomics from the life sciences. I'll be talking about efforts linking suite and ENVO. And finally, I'll go into actually trying to access the functional genomic potential from suite terms. So it'll come full circle, hopefully. Okay, so I'll begin with FAIR, and I understand that some people might grimace when you see this because it is overplayed. However, in my field of life sciences, it's nowhere near ready. So I think that people kind of get hung up on the findable, sometimes the accessible, sometimes the reusable, but the hardest part is the interoperability. And that's something that, at least in my field, is not particularly well understood. And in order to be interoperable, you actually have to read the paper and you have to look at the details. And you find that Wilkinson et al., they highlighted several things. They need really good metadata that uses a broadly applicable language, that uses vocabularies that follow the FAIR principles, and also include qualified references to other metadata. And this is really to be able to make data work together so that we can actually bridge things like life sciences and earth sciences domains, which are not currently realized to its full potential in terms of connectivity. And this is also something that can be done interoperable and findable to not only humans, but also to machine agents that are deployed to access data. So I'll be discussing ontologies because we all love ontologies, or at least some of us do. So what is an ontology? An ontology is a human and machine readable representation of knowledge about the real world. So just as a very dummy concept example, we have some sort of concept like transportation. And then within that, maybe perhaps we have a subclass like personal transportation. And then that could have different types, like a bicycle or perhaps a car. They also exist on the web and are maintained there, and hopefully forever. Ontologies can also be thought of as knowledge graphs that help put data into context for machine agents. So the reason that we use ontologies and we discuss them so heavily is that not all semantics are created equally. There are weaker semantics, such as controlled vocabularies, and stronger semantics, like ontologies, which actually do include qualified references to other metadata, which helps to bring things into a fair and interoperable, specifically interoperable state. So data can actually work together, because when you look at when you work with the data together, the pieces actually will fit together because of these qualified references. Okay. So within the earth science world, as many of you know, there is a great ontology, this suite, which was developed by Dr. Raskin. It's a foundational earth science ontology. Many terms, many ontologies. I'd like to thank again Dr. Raskin and his family, and hopefully this is doing him, not a disservice. So he developed it while he was at the NASA Jet Propulsion Labs, and it's currently governed by ESIP. The suite is it includes quite a variety of upper-level terms, but it represents quite a few environments, such as oceans, the atmosphere, soils, and glaciers. And this is something that earth science professionals typically are using. And so we want to really bridge this to future work, which is in the life sciences. So in the life sciences, the a standard set of ontologies are the open biological and biomedical foundry ontologies, known as OBO. These are, like Suite, a collection of ontologies which are domain-specific and are meant to work interoperably. We have an upper-level ontology called the basic formal ontology. We have the gene ontology, which is highly cited as the most successful ontology in the life sciences. And corollary to that, we have the environment ontology, for which I'm a junior developer. And finally, all of these can be linked together using the relations ontology, which kind of help to bring this whole picture together and hopefully make things interoperable. So moving on a little more about the environment ontology, we also represent a variety of environmental features, materials, etc., biomes, ecosystems. So we have similar terms, actually, to what is in SWEET. Things we can represent oceans, atmospheres, sediments, and glaciers. And within the environment ontology, we have a term such as a glacier. We show its definition, and then we also include qualified axioms that help to make the data interoperable. This glacier has parts of ice, it has parts of snow, etc. So switching gears again and moving into the life science world, I'm going to briefly touch on metagenomics because the point of this talk is to really help to connect the biotic and abiotic. And metagenomics is a field from microbial ecology and medicine in which, relatively new field, in which people characterize microbes, bacteria and archaea, typically, without actually cultivating them. So this relies on genomic information. So you basically can think of it like bulk environmental or medical genomics. The genome of stool, the genome of soil, the genome of water, etc. This has enabled microbiome research, which is, let's be honest, kind of a buzzword in the life science community. This has enabled projects such as the Earth Microbiome Project or the Human Microbiome Project to really make use of this genomic data. So in terms of sources for genomic data, there are two large and rapidly expanding sources. There's the European Bioinformatics Institute, the EBI, hosted in Cambridge and Kingston and Heidelberg, as well as in California, the Joint Genome Institute, both of which contain massive stores of microbiome genomic data. Additionally, both of these sources make use of the same paper to help standardize their data using a controlled vocabulary. Upon examination of some of these data available from these sources, we find that they have data for things like glaciers, which we can help to represent within the environment ontology with terms. So discussing a little bit about how we would bring their genomic data into the semantic realm using ENVO, which we will later link to SWEET, we can discuss a term such as a glacial ecosystem. An ecosystem which is determined by a glacier and which contains axioms, again, these qualified metadata to other terms within the environment ontology, such as a glacier or a glacial feature. As a side note, I just wanted to highlight the glacial feature hierarchy, which Dr. Buttigieg and I worked on during my master's research, which helps me to be standing here today. So thank you, Pierre, for that. So in order to, really push this forward, we're trying to employ more sophisticated ontology term generation techniques. For example, we can use these tools called robot templates, which actually help us to generate ontology files from CSVs, which is pretty cool. It's pretty neat. So we can for example, if we wanted to populate these ecosystem terms, we can use this CSV like this with features, materials, etc. And we can create the OWL file, which the ontology is in. And this is compliant with the MIG standards, the minimum information about any X sequence for any life science people who are interested in that. Finally, we can kind of bring together these ESIP and ENVO by these determined by relationships, which have been formalized by Dr. McGivney and Dr. Mungle. Moving forward, we can bring these we are working currently to create the terms by which to really annotate this genomic data.
and then actually lead us to the genomic data from sources such as EBI and JGI. Now, I want to just kind of highlight this as an example. Say you were someone like a glaciologist who's used to working with data products that are, sweet enhanced. Maybe they want something new. They want something different. They want to access the genomic functional potential, the living space of their glacier. So what we're doing is we're trying to help connect all of this genomic data to the sweet data products. And this is kind of the path in order to do that. And let me just finally kind of give a little demonstration about what that would look like in terms of a little Sparkle adventure. So we can deploy something like a query like this to an endpoint. This is the ontv endpoint. And we can do something, it's actually quite simple. Don't be intimidated by this. I certainly am, but I'll try to walk you through it. We can select something like we want an X, Y, and a Z, where X is some class determined by some Y. Y is something that is the sweet glacier, and Y also has some Z. And what we get out of something like this is we'll get our Envo glacial ecosystem, our glacier, which, as you can remember, is the bridge point, and finally, Z, which is the genomic data hosted by these sources such as JGI and EBI. And this is really what glaciologists, or imagine any situation where the earth scientists can really go forth and dip their toe into and get a hold of this new life, or not new, but newly connected life science data set. So that's what we're really hoping to bring to the community, and we're really hoping to enhance the value of ESIP and SWEET by bridging this gap to the life science world and hoping to make these things work together using these semantics. So with that, I will summarize. Ontologies help to make data interoperable. They enable data to be fair. There's work ongoing to link these earth science ontologies, such as SWEET and ENVO, as you can see in the example. The environment ontology is used for the annotation of metagenomic data, and we're working toward a comprehensive term set to really capture the community's needs. It's mostly there, but we want to make it better. And we're also employing strategies to kind of help automate this process. And then this is really what we're trying to provide, is this access to microbiome data, especially from SWEET products, from institutes, EBI, JGI, et cetera. Not only for humans, but also specifically for machine agents deployed to go and collect all of this data together. So with that, I would like to thank the ESIP committee. Thank you very much to Megan and Aaron, and of course, Dr. Raskin and his family, my collaborators, Pierre, Chris, and Ramona, as well as my PI, Dr. Horwitz, back in Arizona. And with that, I would be happy to take any questions. No questions? Yeah, just please feel free to go to the microphone if you have a question.
So thanks, Kai, for that overview, and it's exciting to see this happen inside a cyber infrastructure that's dealing with so much microbiome data. But this is then the question: we've been working on this on the ontology level, but I'm eager to see results. Do you have any preliminary results to see, like, if you can do environmental compartmentalization of metabolism?
Yeah, absolutely. If you guys want to see this, this is kind of cool. So I have so if you want to kind of take this to the next level, what ends up happening is you can really deploy systems. This was an experiment I did during my master's research, where I kind of went and I set up a little Sparkle system with some genomic data to really, and within the framework of the environment ontology, to be able to ask questions like, what cellular amino acid biosynthetic processes differentiate different types of marine biomes or benthic biomes. And so I kind of set up this little system where you can actually kind of use the gene ontology to parse out these different life science data. And so yeah, you can do some kind of interesting things. So here, shown here, is kind of in light green are the shallower samples, and in dark green the deeper samples, ordinated in their gene space, so their gene ontology term space. This has been extracted from the genomic data, and you can actually kind of see that these different, the deep and the green samples are differentiated. And furthermore, you can actually see that there are certain terms like cysteine, et cetera, leucine, et cetera, that actually help to differentiate these samples. Same with the deeper terms.
So I think it was really interesting the way that you talked about knowledge relationships, capturing the knowledge about these ecosystems. But one of the key aspects of ecosystems is that the members of the ecosystem are actually relating to each other, predator-prey relationships or seed dispersal relationships. So is there any move to sort of capture those ecosystem relationships through corresponding ontological relationships?
There is. I'm not the best person to speak on this, but there absolutely is. We try to axiomatize. Obo tends to over-axiomatize, as some people like to joke about. So we tend to try and capture as many of these relationships as possible. There's ontologies such as the eco-core, ecological systems that kind of captures these predator-prey relationships, etc. And we're trying to, the goal of Obo is really to bring these things together. But what I want to emphasize here really is this connection that we can, from a sweet term, move into the Obo space and then move into the genomic space and really help to bring these fields together.
Can I get one last question? One last question. I'm allowed. Where are the growth areas outside of ontology development across ESIP for this type of work? Where do you think?
The growth areas outside of ESIP.
Yeah. Where are the areas of application into other communities and clusters across ESIP? You see where your work could assist other parts of the ESIP community?
Well, I think that anyone who's dealing with abiotic data that is part of a living ecosystem, that wants that other side to it, that wants to be able to access the living side, the biotic. I think anyone who's working, a glaciologist is the example I used, but I mean, the examples are countless. I know there's marine data. I know there's all sorts of things happening here. So I think anyone who's dealing with something from a purely abiotic lens, perhaps could be interested in doing this and really getting that other side to the story. I hope that answers your question. Thank you.
Thank you again, and congratulations, Kai, on this year's Raskin Scholar. So it's now my honor to set up the introduction of this year's Charles Falkenberg Award winner. The Charles Falkenberg Award is named, surprisingly enough, after Charles Falkenberg, who was a significant contributor to this theme that we have for this year in terms of data to action, as he had a research focus on applications of earth science data, and with a key focus on visualization. And when he, his wife, and daughters were taken from us on September 11th, 2001, AGU and ESIP decided to recognize his contribution to the community through the establishment of this award and awarding the first Charles Falkenberg Award posthumously to him in 2002. ESIP and AGU collaborate in identifying each award winner, and I'm very happy to invite Shelley to come up to introduce this year's Charles Falkenberg Award winner.
Carl did a great job describing the work of Charles Falkenberg, and truly his effort took data to action. And this is something that ESIP is focused on, and really a great connection between AG and ESIP. So our winner, Rebecca Newman, received the Falkenberg Award this last December 12th. Rebecca embodies the purpose of the award, contributing to the quality of life, economic opportunities, and stewardship of the planet through the use of earth science information. She brings awareness to the public of the importance of understanding our planet. As the EOS article announcing the award stated, Rebecca is passionate about combining fieldwork with laboratory analyses, earth science data, and models to discover insights into large-scale societal problems such as arsenic contamination of groundwater in Asia, methane emission from peatlands of the Arctic, and food quality challenges in a changing climate. Her research has resulted in concrete suggestions for policymakers and land use planners, and please welcome Becca Newman.
Great. Thank you for that wonderful introduction, and I'm happy to be here today. My talk is going to be a little bit different than what we've been hearing about. This is more a story about data, providing some very concrete research and policy management suggestions. So I'm going to be speaking about arsenic contamination of freshwater ecosystems, and this is work that I and a number of collaborators have been working on. Turn this on. Great. So arsenic contamination of water is a global problem. Here I'm showing lakes around the world that have been reported in the academic literature to be impacted with contamination of arsenic due to a number of different activities. Today I'm going to be focusing on lakes located here in the Puget Sound region. And these lakes have been impacted by smelting. So the Asarco smelter operated just here outside of Tacoma, Washington for about 100 years. And over this time period ended up emitting arsenic out of its smokestack as a byproduct of its operations. This arsenic blew downwind and then settled into soils as well as into lake bed sediments here throughout the Puget Sound region. Today, I'm going to be focusing on two of the lakes which have been most heavily impacted. You can see that both of these lakes have around 200 milligrams per kilogram of arsenic within their sediment. We have Angle Lake, which is going to be one of our deeper lakes, and then Lake Killarney, which is a really very shallow lake. So when we're thinking about the vulnerability of a system to contamination, we need to understand how that contaminant moves and cycles through the system. So in a lake system, we have arsenic here sequestered into the lake bed sediment. And what can happen is that microbes, as part of their respiration process, when the system becomes anaerobic, can end up mobilizing arsenic off of that sediment and into the pore water, which is surrounding that sediment. Once we have arsenic in the pore water, it can diffuse up and travel up into that overlying lake water. And once we have arsenic in the lake water, it can either associate with particles and basically scavenge and fall back into the lake bed sediment, or it can be taken up into the biological community. So when we're thinking about uptake of arsenic into the aquatic ecosystem, the form or the speciation of the arsenic becomes quite important. So we are talking about inorganic arsenic, which is the form of arsenic that gets emitted into the environment from smelting and mining operations. And inorganic arsenic under more oxidized conditions takes on the form of arsenate. And then when we have more reduced anaerobic conditions, we end up with the species of arsenite. It turns out that when arsenic is speciated as arsenate, it is more readily able to enter in and affect the aquatic food web, and that's because arsenate is a phosphate analog. So phytoplankton, macrophytes, periphyton, they mistakenly take up the arsenate thinking it's phosphate. So that's the way that this enters into the food web. In addition, you'll notice this arsenate has a negative charge on it. So this means that it's a more particle reactive species. So this arsenate's going to be more likely to attach onto particles, and then these particles can actually get stuck onto the outside of insect bodies. Once we have arsenic then entering into the bottom of the aquatic food web, it can move up and begin to affect the higher trophic levels. Today, I have just a little bit of time, and I'm going to be focusing really on the uptake of arsenic into phytoplankton, this kind of first entry point into the aquatic food web. This is a really good key indicator of bioaccumulation. Okay, so the really interesting result coming out of our work in this study system is that it appears that shallow lakes are more vulnerable to contamination than deep lakes. And so what I want to do now is step through all of the data that point out this interesting result. The behavior is largely driven by thermal stratification. So I'm showing here temperature measured in our two lakes as a function of depth within the lake over time. And we're going to be focusing just on the summer months here highlighted by the gray bars. Summer is really when all of the action is happening in our lake system. So the temperature profile here in Lake Killarney, you can see that the lake is staying relatively well mixed over the summer. We have a pretty uniform temperature profile. We do have some periods in here where we get some weak stratification. Here in Angle Lake, you can see that we get strong thermal stratification. So what we end up with is we have warm, less dense water, basically sitting on top of cooler, more dense water. And this creates this thermocline, or a barrier to mixing. So we get a top layer that's well mixed and a stagnant bottom layer. The stratification is controlling the lake chemistry. So here I'm showing dissolved oxygen and dissolved arsenic concentrations measured in the lake. And we see that in Lake Killarney, we are getting the development of low oxygen zones down at the lake bed sediment, but they're pretty localized, relatively transient, and they don't ever go completely anaerobic. Whereas in this deeper lake where we have strong thermal stratification, we get the development of extensive anaerobic conditions. When we look at the arsenic concentrations, we can see that we tend to have higher concentrations down in these areas where we have low oxygen. This aligns with the fact that this microbial mobilization of arsenic, moving arsenic off of sediment and into pore water, is an anaerobic process. But importantly, what you'll notice is that we are getting arsenic here in Lake Killarney moving all the way up throughout the entire water column. And so what's happening is we get high levels of arsenic into these waters where we have dissolved oxygen. In contrast, in Angle Lake, we're getting arsenic sequestered just down in these deep anaerobic waters. Okay, so we'll recall that aquatic life needs oxygen in order to survive, and so we tend to have aquatic life hanging out in water where we have dissolved oxygen. And so this means in Lake Killarney, we're getting a spatial overlap between the contamination, which is making its way up into the oxygenated waters, and the aquatic life. In Angle Lake, we're getting a spatial separation. So the aquatic life is where there's hanging out where there's oxygen, but the arsenic is down here in the anaerobic waters. In addition, in Lake Killarney, because it's an oxygenated system, we have arsenic speciated as arsenate. Recall that that was the form that was able to enter into the aquatic food web. In contrast, in Angle Lake, because all of this arsenic is down here in the anaerobic waters, it's speciated as arsenite. So all of this has a big impact on bioaccumulation. You can see here both of the lakes have similar maximum arsenic concentrations in their lake water, but when we looked at the amount of arsenic within the phytoplankton, we found an order of magnitude difference. This is on a log scale here, and so the phytoplankton in Lake Killarney have an order of magnitude more arsenic in their biomass than the phytoplankton in Angle Lake. So we suspected that looking at maximum arsenic concentrations was not really the best metric for predicting bioavailability. Instead, we thought we should look at the amount of arsenic within oxygenated water. And so here I'm now showing data from 4 lakes. So we have Angle Lake, Killarney, and I'm bringing in 2 additional lakes from our study system. And I'm plotting arsenic measured within phytoplankton against the average arsenic concentration measured within oxygenated water of that lake. The dots here are snapshots in time. So every time we went out to the lake and we sampled the plankton and measured arsenic. The diamonds are giving the lake average over the summer season. And so what we see is that arsenic within oxygenated water is a relatively good metric for predicting bioaccumulation. And I point this out because currently water quality guidelines set for surface water, arsenic contamination in surface water, are focused on that maximum arsenic concentration value and taking no account for the amount of oxygen within that contaminated water. So here's one, I think, clear kind of policy outcome of the work. Okay, that said, it's actually a little bit unexpected to have high levels of arsenic within oxygenated water. And this is because, again, that arsenate ion with the negative charge is very particle reactive. So arsenic tends to get scavenged and removed out of the overlying lake water pretty quickly. So we wanted to understand how are we even developing these contaminated oxic water columns. To answer that question, we're going to move down here and think about the mobilization of arsenic off of sediment and into that pore water. The data I'm showing here are dissolved arsenic concentrations measured in the lake water just above the lake bed sediment and then into pore water as you move down into the sediment profile. So what we see is that in Lake Killarney, we have 25 times more arsenic in pore water than we do in Angle Lake. But why is this the case? I started this talk, I said these lakes had the same levels of arsenic contamination, so they each have about 200 milligrams per kilogram of arsenic within their sediment. How are we getting one mobilizing so much more arsenic into the pore water? We suspected the answer laid in the fact that there is a big temperature difference at this water sediment interface within the 2 lakes. You can see that in Lake Killarney, the sediment water interface gets about 10 degrees warmer than the sediment water interface does in Angle Lake. And this microbial mobilization process, like all microbial processes, is sensitive to temperature and speeds up as temperatures get warmer. To test this hypothesis, we went out and we collected cores from the 2 lakes during the wintertime, brought them back to the lab, incubated them, and measured arsenic concentrations within that overlying water over time. We found that both of the cores incubated at 10 degrees Celsius had minimal to no mobilization of arsenic up into that overlying water, whereas the cores within this warmer incubation both had mobilization of arsenic. You'll notice there's a subsequent loss of arsenic out of the water column, and this is because over the course of the experiment we ended up generating sulfide, and we think we had precipitation of arsenic sulfide minerals. Okay, so we're getting these warmer bottom sediments, we're getting greater mobilization of arsenic into pore water. This greater mobilization is now facilitating more transport of arsenic out of the pore water into the overlying lake water. So we know that Fick's law of diffusion, the flux is being driven by the spatial concentration gradient, and we can see that the spatial concentration gradient of arsenic is much larger in Lake Killarney than it is for Angle Lake. In addition, we have some preliminary data that are indicating that we likely also have turbulent transport processes occurring in the lake, helping to bring arsenic up out of the sediment and into the water. What comes up must come down. And so here I'm now showing you the downward flux of arsenic out of Lake Killarney. This was captured with sediment traps. And as you can see, this downward flux, as expected, is quite large. So here's the maximum for Angle Lake. So Lake Killarney, we're having extremely large downward flux of arsenic. This is expected because of that particle reactivity of the arsenite ion. But when we compare these downward fluxes with the upward flux that we're getting calculated based on this concentration gradient and molecular diffusion, we see that the upward flux is basically exceeding or matching this downward flux. So bringing this all together, what we're seeing in our shallow lake system is that the sediments are getting warmed up. And because of this, we're getting more mobilization of arsenic off of the sediment and into the pore water. It's a microbially driven process. When we have high concentrations of arsenic within the pore water, we get a large diffusive flux of arsenic into the overlying lake water. Within the lake, we're getting mixing, so we're possibly also getting turbulent transport, bringing arsenic into the water column. But importantly, we're getting arsenic mixed up throughout the entire water column, including up into areas where we have oxygenated water. And it's really this arsenic up in the oxygenated water that's enhancing the biological uptake, because we're getting spatial overlap between where the organisms live and the contamination exists. And we're getting the arsenic speciated in the form that's able to penetrate into the aquatic food web. We are seeing a large return flux of arsenic back into the sediment, but this large return flux is basically being offset by the large upward flux. So to conclude, I want to come back to this map that I began the talk with and point out that most of the lakes pictured here globally are large, deep, famous lakes, right? And many of them are experiencing that thermal stratification that we saw in Angle Lake. And so I think that the story that our data is saying is that as researchers, lake managers, policymakers, we should shift some of our attention away from the big, deep, famous lakes towards some of the smaller, lesser well-known lakes. So here I have a picture of Lake Killarney, which I've been talking about. You can see it's a tiny lake. It's embedded in a densely urban area, so it's getting heavy use by people living around it, and it's an important ecosystem, an important urban ecosystem. And our data are indicating that these small lakes, which are often overlooked, are perhaps the ones most vulnerable to contamination. And with that final little plug, I'd like to acknowledge our funding and then the numerous people who helped us in the field collect all the data. And of course, thank the Falkenberg Award and the organization for having me come here to talk. I'm happy to take questions.
Rebecca, great talk and congratulations on the award. I noticed there was kind of a spiky pattern in the arsenic concentrations in the deep water in Angle Lake. Do you have any explanation for why it looks spiky?
Oh, why it seems to have a pulse to it?
That sort of spiky pattern that shows up there, is that a sampling artifact, or do you have any idea of why it's doing that?
Yeah, so all of these data I'm showing here, it's maybe the actual data points that we have, and then everything's kind of interpolated between that.
Okay.
So this and had lower concentrations than like the previous time period we sampled. I don't have a good explanation for that. I think it could perhaps be somewhat related to the same thing we saw in the lab experiment, where we had sulfide generation and then sequestration of arsenic kind of back out of the water column. And so there could be some interesting, I don't know,
If I couldn't cycle through that.
geochemistry and cycling happening within this kind of anaerobic pocket of water.
Okay, thanks. And also, do you feel like you can rule out any new significant inputs of arsenic coming into the lakes from the actual surrounding, terrestrial sediments?
Right. So we have been, I guess we've been talking a lot about doing stormwater sampling. I'm not sure that we've ever successfully managed to carry it off, because we're trying to get our the local partners living around the lake to help us collect those sediments. but I do have one slide showing the historic profile of arsenic within the sediments, and it really, I think, demonstrates, here it is. So this is an example for Angle Lake, and it really demonstrates just the influence of the smelter on the whole system. We're able to, with lead-210 dating, know the approximate date at which different layers of sediment were deposited into the lake. And this is arsenic with arsenic plotted with depth. And so we can see in these older sediment layers, very low levels of arsenic. And then exactly with the time periods during which the Asarco smelter was operating, a big spike in arsenic within the lake bed sediments. That said, the soils in the area also have arsenic, so we certainly could be having continued input with storm events. That's maybe more of an answer than you wanted.
Thank you for your talk. Can you guys hear me?
Yes.
Okay, thank you for your talk and congratulations on your work. It's really interesting that when I first arrived in this area, I heard from locals about the arsenic and the smelting of aluminum affecting this whole area, and that now they're Superfund cleanup sites. And what can actually be done by these Superfund cleanup sites to mitigate these effects? And will your research continue to monitor this and take statistics in the future?
Thank you for that question. So, yeah, these lakes aren't within the Superfund site. So the Superfund site's kind of located right around the smelter in the Commencement Bay Flats area. And so a lot of the soils and lake beds that have been impacted are kind of further outside of the official zone of the Superfund site. There is a good dirt alert program that the Department of Ecology has, kind of helping people understand that their soil around their houses could be contaminated, and that if they want to grow vegetables, they should, put their own soil out and not use the contaminated soil. And they provide free testing. But the lakes, it has been one area that's kind of slipped through a lot of the regulatory cracks. And so I think that's one area that our research has been helping with. We've tried to meet with agencies here in the Washington state area, lake management and other groups, kind of raising awareness around this idea that the lakes have also been impacted with contamination, and we are getting movement of that arsenic up into the aquatic food web. And so in terms of remediating the lakes, it's a little bit hard because there's a lot of small lakes, and you basically have to come in and dredge out all the sediment, which is, kind of a pretty destructive or costly approach. So I think what our research is trying to do is kind of quantify the how much arsenic under which conditions is making it up into the aquatic food webs, up to a point, especially where we are getting it into fish, where people would be potentially, eating that fish. And so focusing more on kind of educating and raising awareness around the topic, and maybe putting out fish alerts for certain lakes. So that's kind of how I see my research fitting into that larger context.
And if you could please join me in thanking all of our plenary speakers this morning. And I'd like to send you to our morning break with a thought related to what we've seen already this morning in terms of the products and outcomes of the application of passion and interest and energy into particular problems and looking at solutions to those problems. And as we go out to our various breakout sessions and we're figuring out what we want to do today and for the rest of the week, I encourage all of you to look at the options you have and follow your passion. Follow those things and engage in those activities that really excite you and interest you, because that's when we do our best work, and that's when we get our best engagement. So with that, go forth, enjoy, interact, and have a great day. And we need to actually separate this room for our breakouts, and they won't be able to move the walls until everybody is out of the room. So please take your immediate conversations out into the hallway where you can caffeinate, hydrate, and talk while they change the rooms. Thank you.
Thank you.